Okay, the material on these slides relates to chapter 3 or 13 of the book. So the subject of this chapter is statistical models for modeling binary choices. Okay, there are many examples in economics which might be considered binary decisions. For example, we may be interested in the decision whether people attend school, whether they go to college, whether they get married, whether they accept a job offer or choose not to work, whether they have a child, or whether they buy a car. So what we're going to do is lay out a framework for studying these binary choices. And then later on, we're going to extend the models to consider more than two possible decisions. Okay, these types of models are called random utility models. So suppose you have some data on the choices that people make. So the data could consist of characteristics of the actual choices, as well as characteristics of the people that are making the choices. For example, if you're modeling transportation choice, and people have the option of driving to work in a car or using public transportation, you may have characteristics of each of the modes. Like, what's the cost of public transportation? How long does it take if you to get to work if you use public transportation? But you may also have things like what's the gender and age of the person making the choice. So we want to be able to study how the determinants of choices that people make, just what are these determinants? Like, for example, if you increase the price, how is that going to influence the fraction that choose public transportation? All right, so let me lay out a little bit of notation. So we're going to have U0I denote the utility of person I if they take a car, and U1I is the utility if they use public transportation. Okay. And we're going to write the utility function as a function of some observables, such as distance, to work, age of the individual, price of that mode of transport. Okay, the z's are going to be observed things, and then the epsilons are going to be random unobserved factors. So the unobservables, it could either just be random psychiatric or just mental processes. So for example, maybe the same person just arbitrarily makes different choices because there's some random process in the brain. Or else the epsilons could just represent some factors that are affecting the individual decisions, but that are not available in the data. Like, for example, suppose that when it's raining, a person drives their car instead of taking the bus. If we don't have rain in the data set, it'll look like it's random, perhaps. Okay, so we can write the probability that we observe a person taking the bus as the probability that the utility associated with that option exceeds the utility associated with taking the car. Okay, so notice how we're comparing the utility from option 1 with the utility from option 2. And because some of these are unobserved, that's why it's considered to be a random utility model. So it's useful to group all the unobservables on one side and the observables on the other side. Okay, now to write down an expression for that probability, we need to make some assumption about the error terms. Okay, so one assumption we can make is that the error terms are normally distributed. Okay, so there are two error terms, so that means they're joint normally distributed. So this is, they have mean 0, and this is their variance covariance matrix. So the difference between two normal random variables is normal. Okay, so therefore the difference between epsilon 0 and epsilon 1 is going to have a normal distribution. And we can figure out the variance is going to be sigma 2 squared plus sigma 1 squared minus 2 times the covariance. Okay, and so let zi gamma denote this zi beta 1 minus beta 0, and we'll let the error term denote the difference in the two errors, and sigma be the square root of the variance. Okay, so now UI divided by sigma is going to be normal 0, 1. So the probability that a person chooses to ride the bus is going to be the probability that Zi gamma is greater than Ui. If we normalize that by sigma, then we get something that's normal 0, 1. Okay, and so this is then the normal CDF, because it's a probability that a normal 0, 1 variable is less than this. Okay, here this, I'm just giving the expression for the normal CDF. Okay, so the parameters of this model can be estimated by maximum likelihood. To set up the likelihood, we need a dummy variable that denotes which choice the person made. Okay, and then we can write the likelihood as, so we're going to have a likelihood for each person, but then the overall likelihood is going to be the product over all people. So here I'm assuming there are n people. And for the people that we see making option 1 choice, we write down the probability that they choose option 1. And for the other people, we write down 1 minus that. So that's a probability they choose option 0. So look in this equation, you can see that gamma always enters as a ratio with sigma. Okay, and that tells you that you can only estimate gamma and sigma together, that you cannot estimate them separately. Because any values of gamma and sigma that give you the same ratio would give the same likelihood. So think about if you multiply gamma by 2 and sigma by 2, you'd get the same likelihood. Okay, so that means that only the ratio gamma over sigma is identified. Okay, so to solve for this, you maximize the likelihood, and oftentimes it's a little easier to maximize the log of the likelihood because it's a little easier to work with. And it's legitimate to take the log of the likelihood because log is a monotone transformation. So whatever maximizes the likelihood, it's also going to maximize the log of the likelihood. When I take logs, that product becomes a sum, right? And then I get di log of the Probit CDF. This is the normal CDF here. Okay, and I put gamma star, and gamma star is equal to gamma over sigma. Okay, and then we take the derivative. So when we take the derivative of the CDF, we get the PDF. Okay, so this is the PDF, and this is the CDF. Okay, and now to get from this step to this step, you just rearrange terms. Okay, so I can either solve for gamma star by maximizing the likelihood directly, or I can solve the first order condition. And we can verify that it's a maximum by taking the second derivative. Okay, I mean, I'm not going to ask you to do that, but you know, this is the way that you could verify it's a maximum. All right, and in terms of the distribution, so we're not going to derive the distribution in class, but there are many different textbooks that provide it, but one textbook is this book by Memia, and this is the limiting distribution of the variance covariance matrix. Okay, so once you have that gamma star parameter, then you can actually form this matrix. Okay, so this would be the corresponding estimator. Oh, actually, it's the same here. This is the estimator. This is actually A hat. All right, so an alternative would be to estimate a Logit, what's called a Logit model instead of a Probit model. Okay, so the Probit model assumes the errors are normal. The Logit model makes a different assumption. Okay, it assumes the error terms are drawn from a type 1 extreme value distribution. And in that case, the difference between the error terms, epsilon 0 minus epsilon 1, follows a logistic distribution. Okay, so I'm going to describe, what the logistic distribution is. So why might we want to use a Logit model instead of a Probit model? So it turns out that the Logit PDF looks very similar to the Probit PDF. It's just that the tails are a little bit fatter. Okay, so it's actually a very similar looking PDF. But the advantage of the Logit is that it has what's called a closed form for the CDF. Okay, so see, if you go back here, you can see for the normal, the CDF here is an integral. So that there's no closed form. You always have to solve that integral to get the CDF. For the Logit, let's see where we are. For the Logit, the CDF has this expression. So there's no integral. So you can actually, find a closed form for the CDF. Okay, so that's one reason why people like to work with the Logit instead of the Probit. It's just a little bit easier to work with, when you take derivatives and everything. For two choices, it's not a big deal, whether you use the Probit or the Logit. But if you have more than two choices, then, the Probit can be prohibitive because then you end up having a bunch of integrals, whereas the Logit is feasible even if you had like hundreds of choices. So that's a big advantage that we'll see later. Okay, and the derivative of the logistic probability. So this will be useful for some of the problems on the problem set. The derivative has this convenient property that the derivative is equal to the CDF times 1 minus CDF times xi. That's if you take the derivative with respect to gamma. So if you solve for if you write out the maximum likelihood, and then you take the derivative to solve for first order condition, you can use this property, and it simplifies very quickly. All right, so this is all the material from chapter 13.